Hello, my name is Frank Karius. I'm a German MVP for Office Servers and Services, and I want to tell you something about Microsoft Office 365, the network story, and some tools and experience I had during last network assessments. First, think about non-technical stuff. Whenever you order something from a local restaurant, you simply expect a hot meal. In the past, it was a restaurant nearby, and now with Office 365, we order something far away from another city. But we still want to have a hot meal, and that's exactly what we are talking about. It only works with the correct streets, with the right transportation tools, and with the right directions. I don't want to go deeper into the Microsoft principles because there are already a lot of good presentations about that. Here you have a link about that you need local breakouts and all that stuff. So let's talk about our environment. Think about a company, maybe it's located in the United States. Think about a remote site somewhere in the world. Think about a home office like my home office, I'm in Germany. My home office user can use a VPN. Other remote users maybe they have their own wide area connection. The company has a carrier to the internet as usual. And then they use Office 365 services, so there's a connection to the Microsoft Global Network. It could be a connection using the internet, which is not so good, and it's much better if your carrier has a direct connection to the Microsoft Global Network. That's something you can ask or something you can simply test. The global network from Microsoft is worldwide distributed in multiple locations. Microsoft claims it's low jitter, has no packet loss, and is quality managed, all of that stuff. If you see that picture, a home office user, of course, has an own provider, which is normally not the same like the company. So he can use another way to the Microsoft Global Network. And if you have a remote site in another country, the other country would also have a different provider for connecting to the internet and to Office 365. And we all know that this is not a good design. So it should not be a normal case that a remote location or even a home user is using the central breakout to connect to the internet and to connect to Microsoft Office 365. Microsoft simply asks you to have a local breakout. That's clear. So far, so good. Let's do something more interesting, because most services in Office 365 are using DNS to find the right entry point, the right location. And the normal setup is a client connects to the local Active Directory domain controller to ask a DNS name. This domain controller may be asking a server in a DMZ, or maybe asking the provider, or maybe a root server. Whatever it works, it runs somewhere to Microsoft and you get an answer for that. It's clear if a remote location is doing the same and something is going wrong. I simply will show you what's going wrong here in this environment. So I'm here located in Germany. I simply do resolve DNS name to outlookoffice365.com. And if you see that, you can see that the name is resolved to alias. The CNAME is also resolved to the next hop, and AMS stands for Amsterdam. So I'm using the entry point here. And now I think I will connect to my company network using a VPN. If I'm doing a VPN, the normal configuration is that my client connects to the central DNS server for all name resolutions and get the responsible answers. Let's do the first test. I simply do a test against the Microsoft server. I simply do a ping to Amsterdam, and you can see I'm about 18 milliseconds, 19 milliseconds. That's the average latency from me to the Office 365 entry point. How can I now show you a VPN connection to US? And I will show you that by using a DNS server in the US. If you want to do that on your own, you can use a web page like that. This lists a lot of DNS servers around the world. So I will simply say my remote location or my main location is in San Francisco and uses this DNS server. So let's do a query against this DNS server. So I again use resolve DNS name and specify a DNS server, and of course I get another answer. I get an answer like, it's still Outlook, but it's forwarding somewhere to San Francisco. And if I use that, for example, and I send a ping to this machine, I think it's not a surprise that it takes much longer than that. So going back to our original picture, if you have a configuration like that, it's not a good configuration. You should simply try to do a local breakout and to try to resolve names along this local breakout. It does not mean that you have to resolve any name to the internet, but you should resolve the Microsoft names. It's the same, for example, as with the home office. Same situation, try to use a local DNS server to resolve Office 365 and only route DNS names from the domains which are internally to your internal server. Another most seen misconception is that someone wants to have a better DNS server. For example, Google, Quad9 and 1111 offers additional services. They promise they have a really quick DNS resolution all over the world. They offer additional services like blacklisting or removing malware sites and all that stuff. But does this affect Office 365? Let's have a look. I do the same query now against my server here again, and you see I'm hosted in Amsterdam. If I do that, for example, against Google, I also get the answer from Amsterdam. Okay, let's do something else. Let's use Quad9, for example. I don't know where they are located. Oh, now I got another entry. So that's Berlin something. And now let's compare, for example, if I'm configuring my DNS resolver to use one of these fancy DNS servers, then I simply do a ping to that, and you can see it's 14 milliseconds. Okay, that's still okay. Let's try how fast we can use Amsterdam. It's 16. So there is a difference like that. Now let's use something else. For example, let's use Quad9. And here I get Frankfurt as answer. So it depends on what DNS server you ask that you get the right entry point. Sometimes you lose, sometimes you win, but the best option is that your client uses the same route like your IP packets to resolve a public name. There's one more thing which might be interesting. For example, if I ask my DNS client cache, I can see all entries and I can see the time to live is not very long. So if I do the same here, you can see it here, the time to live is 4 seconds. I do that again and again and again. And you can see 2 seconds, 3 seconds, 2 seconds. The highest value I have ever seen is 10 seconds. So Microsoft uses an aggressive way to populate IP addresses to the names. The question is, why are they doing that? It helps them to distribute load and it helps them to publish working IP addresses, so to get rid of services which are not online anymore. Very useful that if you have an active DNS management for that. But there's another story which can work. You should know about Anycast-DNS. Anycast is something the most people associate with IP addresses like 225 and so on, used for media, for streaming and so on. But it's also working with DNS. A client connects to a service using one of these IP addresses, and the internet routers are using border gateway protocol to route the traffic. And of course, a carrier can use duplicate links to the same service. Everything is fine. So the client connects and the routers decide which link is up, which link is available. Everything is done for that. But the surprising story now is that you can deploy multiple servers worldwide with the same IP address. Normally, you would complain about that a server should have a unique IP address in the internet. But you can deploy multiple servers in the World Wide Web, and every server has the same IP address, and Border Gateway Protocol is doing the routing, and that works if every server contains the same information. You don't care which server you reach as long as the server will give you the same results. So it's not a problem at all. So you have availability, you have scalability, and you do not have to work with GeoDNS and other things like that. And now let's see which system is doing that with Microsoft. So I have tested some things. I just have shown you that Exchange Online is using GeoDNS. So it depends on what DNS server you're asking. You get a different entry point with different IP addresses. But if you do the same, for example, with SharePoint Online, then you will see something different. I will first resolve the SharePoint public name from my tenant. If you do that, you can simply see, oh, I get a reply, SharePoint 004, something like that. And now I do the same and ask a DNS server in the US, which is pretty easy. Like this, I use the same as in the test before. And what you can see here, it's the same entry point. It's the same address. You see 13 something 9. It's the same here. So I can ask any DNS server worldwide, and I'll always get the same name and the same IP address. So if you do that now and you try to ping that IP address from various locations, it's always fast. So this IP address is not located, for example, in Germany or in Europe. It's located everywhere in the world. The same is working with Teams. The teams.microsoft.com address is also going to the same address. So if I go here to teams.microsoft.com. It resolves to this service. Here SMSH is the entry point here, and here we have the IP addresses. And if I do the same with my location here, I have to remove the server here. Here you see the resolution against the US server, S005msh.net, and that's the resolve against my local German server. It's the same name with the same IP address ranges. So that's a short insight about DNS and how important it is to ask the right DNS servers to get the proper entry point. Sometimes Microsoft uses Anycast-DNS to solve buggy DNS configurations, but for Exchange Online, currently they use GeoDNS, so it makes really a difference which DNS server you are asking. You have just seen something about latency, so let's start with latency discussions. What about latency? I think you all know that already because you are all professionals using TCP/IP. I simply want to start with a small quiz. Think about two endpoints, on one side a PC, on the other side a server, and everything is unlimited in between. No CPU limit, no disk limit, no LAN limit. The only limitation you have is 20 milliseconds round trip time. What's the maximum throughput you can reach? The story is easy. If TCP would be a very stupid protocol, it would happen the following stuff. The client sends one packet with 1500 bytes. It takes 10 milliseconds to travel to the remote site. We wait for the acknowledge going back, so it takes 20 milliseconds to send a packet and get an acknowledgement. If you calculate that, you get about 65 kilobytes per second. TCP is a much more clever protocol and is able to do window sizing. TCP sends multiple packets and gets a single acknowledge for that, or even a selective acknowledge. But that brings us to the problem, how big is that buffer? So the sender and the receiver has to calculate and to negotiate a buffer size. And sometimes firewalls are disturbing that process, and the buffer size is smaller than it could be, or it's not matching, or what else. So one thing is, simply start your Wireshark. Is the calculated window size something you would expect? Is it large enough and not too large and not too small? Please be aware that TCP is very clever here, because if your latency is high, the window size will grow normally. But if packet loss appears, then the window size will go down again. If jitter is in your connection, it will also adjust the parameters. So TCP is always tuning that stuff. Nagel algorithm is something like that. You can see that on Wikipedia. The story is, what's the normal packet size or the normal buffer size negotiated between clients? So I have done a Wireshark and was tracing connections between Exchange, between OneDrive, SharePoint, and so on. And you see they negotiate different window sizes. So it simply depends on the payload. It's everything on the same machine, everything on the same system. It's not a problem if you're in your local network with 1 millisecond latency or even lower. So even if you have a window size from 1 megabyte and you can send 1 megabyte per millisecond, so you can send about 10 gigabyte per second. That's much more than a normal PC can fulfill. But if your latency is a little bit higher, like 20 milliseconds, then you see that's a maximum bandwidth you can reach in an optimal situation. So no jitter, no packet loss, nothing else. And if latency is going higher, for example, then you can see that the bandwidth is even smaller, or the usable bandwidth. And that's only the calculated maximum. Normally it's lower because you will have packet loss. And if packet loss appears, you can see things like this. If you have, for example, here 0.1% packet loss, somewhere about here, then your bandwidth is no longer 12 megabit, it's only half of the amount. Packet loss can really be an issue. I will show that to you a little bit later. Packet loss for TCP means the TCP stack has to resend that stuff. In a VoIP world, audio, video, and we use UDP, the system, the endpoints are available to detect that and adjust their data rate. For example, reduce from wideband to narrowband, reduce the screen resolution, the video resolution from full HD to VGA. But if latency and throughput is a limit like that, how can Outlook and other programs use the full bandwidth? How can you use the fiber to the home if we have this limitation? Yeah, the trick behind this to use multiple TCP connections. So Outlook, for example, can use different TCP connections for new emails, for sending emails, public folder access, address book access, delegate access, all that stuff. And every connection has its own window size and its own data feed. A simple FTP to download a single file could be a slower protocol. If you use HTTP or web browser and using different chunks or different ports, different connections, then you can use a much higher bandwidth than you want to have. If you use multiple connections, you run into another problem. Source ports. If you're running your network and you have a private network, which is normally the case, and you have private IP addresses, then there must be some kind of translation from your private network to the public internet. So your private IP addresses are hidden behind 1 or 2 or 3 public ports. And the first question is, how many source ports can a firewall use? And how many persistent connections are used by your clients? How many connections does Outlook use? 10 connections, 20 connections, 100 connections? Who knows? That's something you should measure, or you should estimate. How many clients can you hide behind one IP address? A single source IP can offer up to 65,000 ports. Nothing more. That's 16-bit. That's the maximum number of ports you can have. So if you have a lot of clients behind the same public IP address, you could run into problems, because these sessions are long-running connections. It's no longer a web browser serving the web, downloading a file, and then sleeping, and the user is reading stuff. Outlook maintains the connections, keeps it active. Teams keeps the connection active to get the feedback from the server. Outlook OneDrive keeps the connection active. So we have a total other different workload on your internet connection, on your firewall, on your proxy servers. They have to run a lot of connections which are running 8 hours or even longer. So think about a normal client with Outlook running 20 connections, 10 connections for OneDrive, 10 connections for Teams. So you have 40 connections for a single client. So if you have your 1,000 clients, you eat up 40,000 connections. If you only hide them behind one public IP, you could run out of ports. One important thing for you: ask your firewall admin or your proxy admin if they can monitor the connection uses. And that's my company in Germany with about 100 employees, about 50 are on site. And you can see during the normal work hour, the number of used ports runs from 3,000 up to 7,000, so about 4,000 ports during the normal busy times with 40 users. So we have about 100 connections per users, which are active on our firewall. That needs resources, memory, CPU load. So monitor your source. If you want to know how many connections you currently have, you can use the Exchange on-premise server. Simply get the TCP connections on the Exchange servers, write them to a CSV file, and then use something like Power BI to analyze that. Here's a sample from 8 Exchange servers from a customer with the current connections. And you can see, oh, this server looks like that server has a problem because it has a much lower connection than all the others. In that case, it was a misconfigured load balancer. By the way, that's one of these funny findings. If you have the information about source IPs, client IPs on client ports, then you can build graphics like that. So that helps if you're on premise, which location is a candidate for a local breakout or is a priority candidate, and which connection can still use the VPN because there are only a few clients. Things you can find out like that. You can also get other things like which clients are using how many connections. So who are the archiving solutions, the voice solutions? Is there any kind of misbehavior? Sometimes you find funny things like this in a custom environment. This was a rogue access point. So someone deployed a simple access point to hide 10 other wireless clients behind one private IP. Everything you can find using that data. So let's talk about measuring the highway. So in the past, we had our private wide area links for a client connecting to my Exchange server. Then we had our internet breakout for connecting to the internet. We have our servers, everything was under control, and we also had clients, we could control that. As you can see, our cloud service is number 1 and is managed by Microsoft. Nothing you can monitor really. We have no local traffic anymore between our sites because the local Exchange server is gone. So we save some bandwidth here. On the other side, traffic through the internet is traveling through a carrier, but the carrier normally does not disclose any information about his infrastructure and his performance. That's some hidden secrets. And we see a lot of traffic on our internet gateways going to the cloud. And then we have some internal links with switches we can monitor. But as you can see, there's a problem. The traffic from the client goes to your firewall, leaves your environment, travels through the dark hole of the internet to a dark hole of service. But if the user complains about performance, it's up to you to monitor or to tell them what's going wrong. Most of the time, the network operating center for customer tells me everything is fine, everything is fast. No, we don't have bandwidth problems. And they show me funny pictures like these to show me everything is fine. We have a lot of bandwidth available. The problem with that, it's not a proper monitoring for cloud services and not even for VoIP, because they measure every minute the packets in, packets out, byte in, bytes out, though they are blind for short-term outages or oversubscriptions for a few seconds, which will drop audio video quality and all of that stuff. So it's not sufficient for cloud monitoring. Well, how can we make that better? We can use ping, for example. Okay, I could use a standard ping, which is fine. So if you do use a ping with a larger packet size, but keep in mind, ICMP is not optimal. Sometimes DOS, denial of service protection, kicks in and drops packages. We have carriers who optimize ICMP answers to make you as a customer happy. So I wrote my own PowerShell script to do these pings and show it on a graphical map. It helped me a lot in customer engagements to find out outages which happens regularly or which are based on a site. And if you have multiple clients and you run it on every client, it's very easy to compare the graphics. I will do that for you, for example, with the Bellevue Hotel in the MVP Summit 2019. That's in the late evening, 11 p.m. and that's morning, breakfast time. Someone is doing some large downloads and I can see packet loss with my ping. That's the same in a hotel in Frankfurt. That's the ICE, the fast train in Germany. Don't talk about latency if you use mobile connections. And that's my DSL connection at home during that time frame. And it was pretty clear that something happened during this time. 2 children came home and started using their PC. So that also affects my latency. That's a Microsoft guest network. Everything is fine. So ping works really nice. Even carriers are doing latency tests. So latency is the new oil like data to get a better insight about your network. But it's ICMP. So what's with HTTP? Let's do HTTP. First, we have to look for some URLs we can ask. For example, they should be available without any authentication and they should not be a throttling on the remote side. And I found some of these who looks like pretty nice. You can simply use PowerShell commands like invoke web request to get that. Don't forget the process preference to make it silent, and so it will not disturb your measurement. And if you do that, you see the same in Frankfurt. It's a little bit slower if you compare to ICMP. So an HTTP request takes longer because favicon is a 7 kilobyte file. So 7 kilobytes takes longer than a small ping. That's true. But interesting is if you go to Bellevue, you can see something happened here. And if you compare it with ICMP, then you can clearly detect ICMP detects packet loss or packets are not arrived fast enough, so we handle them as loss. And TCP is able to recover from that situation, but throughput was minimized. So you can, with TCP, you can detect it a slower connection, but you can't detect what's the root cause about that. So you have to monitor both, which helps a lot in that environment. This is a measurement of a big file. And it was amazing on that customer side that sometimes it takes about 5.6 seconds to download that file, which is about 1.3 megabit. And sometimes it takes less than 1/10 of a second to download the same file. By the way, no caching in between, HTTPS, no proxy, no breakout. So this WAN link is it's jumping in the bandwidth. So no control here. Small hint, I have done the same with the testing tool. That's the SNMP monitoring to see the bandwidth is occupied and then I release it. I do the same with the HTTP request. Everything looks fine. And the reason for that is we were able to deploy a bandwidth guarantee for HTTPS for Outlook traffic. So that means this small bandwidth here on these 10% are not used for the full load because Outlook traffic is filling up this bandwidth. So is it better to use EWS? Can we use Exchange for that? Long story, short answer, it does not make sense to monitoring to the Exchange mailbox. I wrote a script to do that every second to get the number of new emails and the results were not really better. But I had some other findings, like I was able to grab the backend servers and two front-end servers. So if I have done that, the funny picture was like that. My client gets the first answer from a front-end server, which is always the same. So there's some kind of affinity. And there's a middle server in Amsterdam redirecting the traffic to the backend server. So in the cloud, I have a cascade from two front ends and one backend, and you can see the latency in between. More interesting, if you use the first two letters, that's the location, and if you put that into a map, then you can see that was December last year, 2019, when data centers in Frankfurt and Berlin were going online, because that was December the 3rd, and then 4th, 5th, and 6th. And you see this part here, that's one client. This client was served from Amsterdam and from Dublin and from Vienna, but then Frankfurt and Berlin appeared. So it looks like Microsoft uses DNS round robin to forward my client to different front-end servers wherever they are. So let's see what's with VoIP. VoIP means we have low latency, low round-trip time, and no tools to measure that? No, there are tools like the Skype for Business Network Assessment tool. You can simply run it. That's how it looks like. It's a command line driven application. It simulates a voice call. You can modify the configuration file, num iterations. If you put them to 13, this tool runs about 5 minutes and simulates a lot of voice calls and then writes it to a CSV file, and you can use the CSV file to pass it into your preferred monitor solution. And so you can get a continuous monitoring for a single voice call for audio. That's funny, I have done that with PowerShell too. So that's a tool end-to-end UDP, doing UDP turn requests to the turn server from Microsoft, which is much more information like continuous test. I can see more packet loss. I can see the minimum, the average, and the maximum round trip time, and also the time to live. And that's what I can see here in my monitoring. So that helps me much more to find out about the performance from my local system up to the turn server from Microsoft. Back to the summary. I hope you understand that latency is a much better quality probe than bandwidth counting and your uplink. So SNMP is great if you monitor your switch or your firewall or your uplink. But SNMP has no idea how you can monitor your performance to Office 365, Microsoft 365. It makes no sense to monitor a service itself. You can't monitor thousands of Exchange servers in Exchange Online. You have only a single mailbox. Even if you monitor every user, they are distributed wherever they are. The same is with OneDrive and SharePoint. But you can check the connection from your side to the entry doors in Microsoft, and that's something you should deploy in your topology. And compared with the sample, think about a transport agency. You're running trucks to deliver packets from A to B, and they are traveling on the highway. Does it make sense to monitor your door where the trucks leave your area? Is it useful to go to a bridge or to a connection and count the cars there? That does tell you nothing about a traffic jam 20 miles away. So all you have to do is let small packets travel through the cloud and back and measure the latency. That makes much more sense to detect outages and so on. I hope you had some fun. If you want to get in contact with me, that's the email address. By the way, it's also the Teams address. Maybe see you at the next event. Bye.